All right, today we'll talk unidimensional. If I can write. Unidimensional optimization. Okay, unidimensional meaning we're dealing with just functions of one variable, not like several variables, just one variable at a time, right? And optimization, this just means finding a local min or a local max. That's when we talk about optimizing something, this just means finding the local min, minima, or local max. Of some function, okay? Okay, so in the context of statistics, can you guys think of any situations where we want to maximize a function or minimize a function? Think of maximizing something in the context of statistics, how this might be useful to us. Maybe, what's that? Maximum likelihood, yes, excellent. Okay, so application could be maximum likelihood estimation. You guys, the other class wanted a refresher on MLE. Are you guys good on MLE, or we want a refresher? Okay, we want a refresher. Okay, sure, I'll give you a refresher, no problem. Okay, what about minimizing something? Something where you want to find the smallest or the least amount of something. Yes, OLS, ordinary least squares regression, or anything like that. Yeah, so OLS. So this would be something like least squares regression. We're trying to find the value that provides a minimum. So here we're trying to maximize something. Here we're trying to minimize the squared residuals, right? So these are common uses of optimization. All right, so let's just take a look at maximum likelihood estimation. And okay, so basically for MLE refresher, the idea here is we're going to estimate the properties of our model, the parameters of our model, by trying to maximize the likelihood. That's, maybe that wasn't helpful, but we want to estimate parameters of our model by trying to maximize the likelihood of our data. All right. Okay, well maybe we'll start with a real example here. So let's say you got data coming from some kind of binomial situation, by a binomial model, right? So you know, you gather data, and as far as the situation goes, either the data is either going to belong in category A or not category A, right? Or it's, you got successes and failures, whatever you want, right? Flipping a coin, asking somebody if they're going to vote yes for a certain candidate or proposition, whatever it might be. You have successes or failures. Okay, so we'll say X comes from some binomial model. Okay, and so maybe our X is going to be some vector of values, and the summary is going to be, I don't know, we'll say 100 observations and we will say 64 successes. And so in our case, we want to know what is the value of P that will maximize the probability of seeing this data, right? What value? Now maybe we already know the answer, but what value of P maximize probability of observing our data? Okay, so I'll flip to the next slide. So in the binomial model, so with the binomial model, we have a PMF, probability mass function. PMF, this is kind of the probability for the binomial. This is basically what? N choose X with P raised to the X and 1 minus P raised to the N minus X. I'm hoping it looks familiar. Okay. And so, you know, traditional use of the PMF would be something like we do 100 trials. You know, each trial has P equal to 0.7 of success, and we ask what is the probability we get 64 successes. Okay, or you know, and so in this case we would have 100 choose 64, 0.7 to the 64, and 0.3 to the 36. And that would be our answer. And the PMF is basically a function of X. It's the probability of X given that N is equal to 100 and P is equal, in this case, 0.7, right? And we would say, and basically this is 100 choose X, 0.7 raised to the X, 0.3 raised to the 100 minus X, if we want to calculate for other values of X. All right, is this okay so far? This is just using the binomial PMF, the mass function, right? And then, so here X can be any value between what? Any whole number between 0 and 100. And if we sum all of the X's, sum all the probabilities of X's, what would we get? We'd get 1, right? You sum all the probabilities of a probability mass function, or you integrate a PDF, you get 1. That's like the rule, right? So if it's for a continuous variable, integral of the PDF over X is equal to 1. Okay, so that's that. How is a likelihood function different from just a probability density or probability mass function? How's the likelihood different? Okay, the probability mass function is a function of what variable? It's a function of X, right? We plug in the different outcome and we say, what's the probability of getting this particular outcome, right? So the PMF is a function of X. Okay. The likelihood is going to look very, very similar, except, so here, let me just back up. So the probability PMF is a function of x, and what is given, we are given the parameters. In this case, n equal to 100 and p equal to 0.7. That's what we have. So the PMF is a function of x, and we are given the parameters. With a likelihood function, it is a function over the parameter values, and we are given x. Okay, so here we have the likelihood function over the different possible values of p, which in this case is going to be the probability that x equals 64 given some value of p and n equal to 100. Okay, and so this will look like 100 choose 64, p raised to the 64, and 1 minus p raised to the 36. This looks very similar, but the thing that's different is that it is not a function of x, it's a function of p. And we're asking, what is the probability, or in this case, what is the likelihood of my data if I plug in different values of p? Okay, so the probability mass function was, what's the probability I get this outcome, okay, if I'm given these parameters. N is 100 and p is 0.7. Okay, now we're asking, if I have this outcome, and how will my probability change if I alter this variable p? That's what we want. Okay, so it's similar, but it's different. And so the likelihood function, this is only defined across all possible values of p, which in this case is 0 to 1. And so p is continuous, and we can vary p, on a continuous basis on the interval 0 to 1, whereas x had to be whole numbers between 0 and 100. Okay. And the integral of the likelihood function of p over all values of p, does not have to equal 1. Right? That's not as important. Okay, but here, so the original, earlier on we said, what's the probability I get 64 successes if I do 100 trials and p is equal to 0.7? No, 0.7 here, okay? And so if we do that, we say, okay, the probability of getting 64 successes is 0.03619. And we could have asked, what's the probability that I get 68 successes or something like that, right? But what we're doing now is we're not changing the x, we're changing the p. And we say, okay, well, what if the probability of a success wasn't 0.7? What if the probability of success was 0.6? Okay? And we say, oh, you know what? That's actually a little bit higher, 0.059. And what we want to do is we want to find what value do I plug in here that will give me the highest probability or the highest likelihood. Okay, so what other value should I try? Okay, well, let's just try 0.61. Okay, and we get something a little bit higher, 0.68. If I plug in 0.62, I get something even higher, 0.076. At 0.63, I get 0.081. At 0.64, I get 0.083. And at 0.65, I get 0.081. Okay, so it seems like, you know, trying out different values, this gives me the highest. And we can try, you know, try to refine this. We can say, okay, well, what about 645? Okay, you know what? This is still a little bit higher than this. And we can try all sorts of different values of p. And what we're going to find is that 0.64 is going to give us the highest value here. Okay, but you know, this is kind of like a guess and check method. And so, you know, we can try different values of p. You know, with the hope of finding the p that maximizes the likelihood of our data. Okay, and that is the maximum likelihood estimate. Okay, so does that refresh your memory regarding maximum likelihood estimation? Yes? Great. Maybe. Okay, and so we can use optimization methods to try to find the value that maximizes the function that we're looking at. Okay, in this case, the function that we're looking at is the likelihood function, which would be this thing, and we want to find what value of p maximizes this thing right here, right? Okay, and then so from stats 100b, you probably had to maximize functions analytically, right? Yes, no? Maximum, so you probably found that the maximum likelihood estimate for a binomial is going to be x over n. P hat is equal to x over n, and yeah, no? Okay, so you know, we optimize analytically. All right, and how do you optimize a function analytically? How do you find a local maximum or minimum in an analytic fashion? Was that derivative, right? Okay, and what do we do with the derivative? So we have the likelihood function of p being 100 choose 64, p to the 64, 1 minus p to the 36. And what do? Okay, we take the derivative. Okay, so we have L prime of p or something. And what do we do with this derivative? We set it equal to 0. Take derivative, set it equal to 0. Solve for p. Okay, and then this would give what, the critical values? Critical values, which will either be a local min, local max, or a saddle point. Okay, and probably if you tried to take the derivative of this, you probably ran into some problems. So we would say, well, if you can't take the derivative of L of p, then work with the log of the likelihood, and you would get log of whatever this is times, I'm sorry, plus 64 times p. Wait, 64 log p? No. 36 1 minus p. Okay. All right, and you set this thing equal to 0, and then yeah, you solve this and you find, you know, p is equal to 64 over 100, right? Okay. Or you take, sorry, yeah, 64 log of p and log of this, and then you set, sorry, you don't set this to 0. You take the derivative of that, and then you get p hat equal to 64 over 100. Okay, so you did that analytically. We can, instead of having to take, to try to solve for this thing analytically, let me clean this up because this is a mess. We can just apply our root finding methods, all right? Okay, so this gives us the log likelihood. You take the derivative ddp of the log likelihood, set it equal to 0. You solve for p. You get 64 over 100. Okay. What we can do is we can use our root finding methods. Okay. So if we want to optimize some function g of x, we find the derivative of g of x, g prime of x, equal to f of x, and then use a root finding method on f of x. Okay. So on Monday, we covered all of those root finding methods, how to find where f of x is equal to 0. And we're just going to extend this, and we're going to say, all right, let's say you want to optimize some function g of x. Well, instead of working directly with g of x, we take the derivative, and then we find the roots of the derivative. Okay, and so the roots of f of x will be the critical values, critical points of g of x. Okay, again, which will either be a local min, local max, or a saddle point. And that's pretty much it, okay, as far as our first family of optimization tools go. Okay, so probably the most commonly used one will be Newton-Rapson method, because usually if you're forced to take the derivative to use this, you might as well just take another derivative, okay, and then you can use Newton-Rapson. But that's what we have. Okay, so we have Newton-Rapson. All right, so Newton-Rapson for root finding, how did that work? So if you had some function f of x, the algorithm was the next iteration, you take your current iteration xn, and then what do we subtract? F of x, the rise divided by the slope, right? Okay, so Newton-Rapson for optimization So let's do, we want to optimize g of x, okay? And we'll say let g prime of x equal f of x. And we would use the exact same thing above, right? So use the exact same algorithm. So if g prime of x is equal to f of x, then all we have to do is find the roots of f of x. Okay, so we have xn plus 1 is equal to x of n minus f of x over f prime of x. Okay, or in terms of g, xn plus 1 is equal to xn minus g prime of x divided by what? G double prime of x. And that's exactly all you do. So we're just extending our root finding method by saying, let's take the root of a derivative, and that's got to be a critical point. Right? The only assumption is that you're able to take the derivative, okay? And that requires a smooth function, right? And in this case, g double prime, so the second derivative has to be defined. And not 0 at the minimum, but or maximum. Okay, maybe is that okay? Do I need to write like pseudocode, or are we okay here? We're okay. All right. So I mean, pretty much the pseudocode that works for root finding will be here. Okay. Except now here. Just the only change is that your function g, it should return. You have all of these other things, and what it needs to do, it needs to return 3 values. It needs to return g of x, g prime, and g double prime. Okay. And then in the algorithm, basically x new will be x old minus g of x, and you will take the second value divided by g of x, and you'll take the third value, right? So because the second value will correspond to g prime, and then the third value in the vector that the function returns will be g double prime. So you just need to have this somewhere in your algorithm. Is this okay? Okay. Okay. I ran out of time in the other class, but maybe I'll get through it here. So, so that's the any of the other root finding methods also work, but I just did it for Newton-Rapson. Here we're going to have kind of a strictly numeric method. And this will be, this is called the golden section search for optimization. So it's kind of using a bracket method, but so do you guys remember the golden ratio? What's the golden ratio? So the idea being that you have some box X, and if you tack on a thing of 1 here, then the ratio between 1 and x, the ratio between these sides of the thing is equal to the same as x over x plus 1. Okay, so the ratio between the the short and the long edge of this square, or this rectangle, is the same ratio as the short and long edge of this rectangle here. Okay. All right. So this is known as phi, and it's like 0.618 or 1 point, whichever one you want to use, or 1.618. Okay, because the idea being 1 over 1.618 is the same as 0.618 ish. Okay, and this will all and this works. What we're going to do is kind of our guiding principle is that if you have some function like this, I need to make this a little bit smoother. Can I make this? I don't know. Okay. If we have some value, if we got a bracket A, B, and C, okay, and if so C is in between A and B, and the key here is that the function C, the function at location C is less than the function at location A, and the function at location C is less than the function at location B. Right? So here's f of B, f of C, and f of A. Okay? And if this is the case, then there must be a local min between A and B. All right. Not necessarily at location C, but we do know that if you've got A and B and C is in between A and B, and the value of C, the value of the function at C is less than the value of the functions at A and B, then there has to be a local minimum somewhere in the interval A to B. Okay. So we're going to use this as kind of our guiding rule in the golden section search. Okay. I'm going to show you the code for a minimization algorithm. If you want to use it in a maximization situation, all you do is you minimize the negative of the original function. And if you minimize the negative of the original function, you just multiply the original function by -1. You minimize that, you've maximized the original function. Okay, so so to maximize, apply the minimizing function. Or minimizing algorithm to -1 times the function. All right, so how's this going to work? What we'll do is we'll I don't know what's going on here. All right. Let's say we've got some function like this, and I'll call this L and R, and we'll have A and B, okay? And B this is 0.618, or the kind of the golden ratio of the distance from L to R. Okay, and same is also true here. So basically B is going to equal L plus 0.618 times R minus L, and A is going to equal R minus 0.618 times R minus L. This is what we have. Okay, and then what we do is, so we evaluate the function at L, and we find the function at R, and we also find the function at A and the function at B. And in our picture, we see that a function at A is lower than the function at B. Okay, so the function at A is less than the function at B. Okay, and so what this means is that L, A, and B form a trio of points where we know, because L is between A and B, and the function at A is less than the function at L, and the function at A is less than the function at B, we know that there has to be a local min between L and B. Okay? So, okay. And what we then do is we just we throw this away. Okay. And so this now defines. So now we have an interval, L, A, and B. Okay, and we know that A, because A is less than the function at A is less than the function at B, we know there has to be a local min between L and B. Okay, and we don't have to worry about the spot between B and R anymore. All right, is that okay? All right, and we iterate this. Okay, and then so now, so B becomes the new right boundary. Okay, and this is the reason why we bother with the golden ratio. Is that when we do this, right? So if I have, let's just use simple numbers, 0, 1. Okay, A is going to be at 618, and here we have at 0.382. Okay, when we do this, and I throw away this region here, okay, so now my interval goes from 0 to 0.618. This location, 0.382, is 0.618 between 0 and the new boundary, okay? So because of the golden ratio, this is 0.618 of the way to our new R. Okay, and then so I only have to find a new location down here. I know my picture's not accurate, but so if you multiply 0.618 squared, you're going to get something around 0.382. Okay, and then on the other hand, going the other way, we would have a new location at around 0.236. Okay. And the advantage of this is that so if this was A, the old A becomes the new B. And now I just have to find the new A. Okay. This means I do not have to recalculate 2 points at every iteration. I only have to recalculate 1 point. Okay, because what we're doing is we're taking an interval and we're finding the values at kind of 2 points in between. And at each iteration, I don't have to redo 2 points. I keep one of them, and I only have to find one new point. Okay, and so that cuts our computation time down, right? Okay, we'll end here for today. I guess we'll wrap this up on Friday, and we'll continue talking optimization stuff.